ancient times, humans gathered around the flickering light of a solitary campfire, their imagination stirring with thoughts of what might be lurking in the surrounding darkness. In many ways, that curiosity remains unchanged. Today, our campfires have evolved, no longer confined to wood and flame but now embodied by telescopes like the James Webb, peering across the globe and into the furthest reaches of the observable universe. Yet, even with this vast reach, there is still a boundary where light fades into shadow, leaving our imaginations to wonder what lies beyond. This boundary isn't just conceptual, it's a physical edge of the observable universe, a horizon where space is expanding so rapidly that not even light can cross it back toward us. Nothing beyond this point can interact with us causally, rendering what lies beyond an enduring mystery, forever out of reach. Or so we believed. In 2008, an astonishing discovery shook this assumption. Hundreds of galaxy clusters were observed drifting toward this cosmic edge at speeds faster than current science could explain. It appeared as though something beyond the horizon was pulling them, or had once done so, with a gravitational force stretching across billions of light years. This mysterious phenomenon was given a name, dark flow. What exactly is dark flow? What could be causing it? And how does it challenge our understanding of cosmology? Now you're watching University of Universe. Today, we'll explore the enigma of dark flow and its potential to reshape our theories about the origin of the universe. Dark flow is a highly debated topic, so let's start with what we know. In 2001, NASA launched the Wilkinson Microwave Anisotropy Probe, WMAP, to map the cosmic microwave background, CMB, the faint radiation left over from the Big Bang, permeating all of space. By 2010, the map was complete, significantly advancing our understanding of the universe's shape, composition, and structure. Key questions were addressed. How flat is the universe? How much of it consists of matter, and dark energy? One scientist, Alexander Kashlinsky, saw an opportunity in this data. Leading a team at NASA's Goddard Space Flight Center, he sought to compare the CMB map with the motion of galaxy clusters. They aimed to detect any patterns using a subtle phenomenon called the kinematic Sunyaev-Zeldovich (KSZ) effect. This effect occurs when CMB radiation gains a slight energy boost while passing through a moving, high-energy galaxy cluster, allowing scientists to infer the cluster's motion. The challenge was that this energy shift is incredibly small, requiring observations of thousands of clusters and extensive statistical analysis to detect. After comparing over 1,000 galaxy clusters with the CMB, Kashlinsky's team discovered an unexpected result, a large-scale motion of clusters spanning 2.5 billion light-years, moving at 600 to 1,000 km/s in the direction of the Centaurus and Hydra constellations. The perplexing part? There's nothing visible to explain this motion. This led to the hypothesis that an immense gravitational source, possibly beyond the observable universe, might be pulling these clusters. The idea that something so massive could exist just beyond our reach is highly controversial. But is it even possible for something beyond the universe's edge to influence us gravitationally? Intuitively, you might think not. As I mentioned earlier, anything beyond this horizon should be causally disconnected from us due to the universe's rapid expansion, which outpaces even the speed of light. Yet, there's a potential loophole: cosmic inflation. This rapid expansion, occurring shortly after the Big Bang, suggests that all regions of the universe were once in contact. If a dense mass existed just beyond our current horizon during this period, its gravitational influence could have initiated the movement we now observe as dark flow, before cosmic inflation pushed it beyond our view. This theory, however, challenges our understanding of the universe as homogeneous and isotropic, raising profound questions about the true nature of the cosmos. Could the universe be far less uniform beyond our horizon? And if so, what does that mean for our models of cosmic evolution? These questions remain unanswered, fueling ongoing debate within the scientific community. However, there's a potential loophole: interaction before a period known as cosmic inflation. For those unfamiliar, This idea arose in the 1970s as scientists grappled with a puzzling question: why does the universe appear so uniform, flat and nearly identical in temperature and mass distribution, even across regions that could never have interacted? This puzzling phenomenon is called the horizon problem. Imagine the farthest observable regions to our left and right. They're remarkably similar, despite having never been in contact. There seemed to be no reason for this uniformity. Enter Alan Guth, an American physicist who realized that this problem could be resolved if, in the earliest moments of the universe, everything was in close contact, allowing it to mix and even out, like dye dispersing in water when shaken. However, for this theory to work, there needed to be a period of rapid expansion, a burst far beyond the already fast Big Bang. This event, cosmic inflation, is thought to have occurred just after the Big Bang and lasted for an unimaginably short time, around 10 superscript 3 seconds. Despite its brevity, during this period, the universe expanded by a factor of 10 superscript 2, a scale likened to stretching from the size of a bacterium to that of the Milky Way in a fraction of a second. This rapid expansion explains how different parts of the early universe could have mingled before becoming separated by vast distances. The concept also introduces complex ideas involving scalar fields and a false vacuum state, but for our purposes, the key point is this: dark flow might be linked to something that happened before inflation. If, in this early phase, a particularly dense region existed beyond what is now our observable universe, its immense gravity could have pulled on our region, imparting motion to galaxy clusters. When inflation occurred, this dense mass would have been flung far beyond our current horizon, leaving the clusters still drifting in that initial direction, carried by inertia, a concept known as going with the cosmic flow. However, this idea is controversial for two main reasons. 1. The need for extreme mass beyond the horizon. For dark flow to exist, a massive gravitational source just beyond our visible universe is required, an enormous concentration of mass far greater than what current models predict. This contradicts the entire reason behind Guth's cosmic inflation theory, which aims to explain the universe's homogeneity. The universe we observe is uniform and isotropic, mass is evenly distributed, and velocities largely cancel out. Dark flow challenges this, suggesting that beyond our visible horizon, things may be less uniform, implying a dense mass we can't see. This raises profound questions. Did we just get cosmically lucky to find ourselves in a particularly flat and uniform patch? If the wider universe isn't homogeneous, what does this mean for our foundational theories of the Big Bang and inflation? 2. The possibility dark flow doesn't exist. The second issue is the potential non-existence of dark flow. While Alexander Kashlinsky and his NASA team stand by their findings, the European Space Agency's Planck mission provided a more detailed map of the cosmic microwave background, CMB, using a more advanced probe launched in 2009. After analyzing 1,000 galaxy clusters, the Planck team reported no evidence of dark flow. However, Kashlinsky's team re-examined the Planck data and claimed they still saw signs of it. The debate remains unresolved, with Kashlinsky's team planning further analysis, but no definitive conclusion has been reached. Until stronger evidence emerges, it's reasonable to remain skeptical of dark flow. There may be no colossal force lurking beyond the cosmic horizon, dragging thousands of galaxies. Yet, the mystery lingers. Science doesn't seek convenience, it seeks truth, however simple or complex. One day, we may finally discover what lies beyond the visible universe and whether dark flow is real. But even then, the darkness will only recede slightly, revealing new cosmic boundaries and new questions. And so, our pursuit of knowledge will continue, because the human desire to explore and understand the unknown is endless. Thank you for watching. If you enjoyed the video, please press the like button, and if you're new, please subscribe and turn the notification button on, so you don't miss our future videos.